This conference will now be recorded.
Hello everyone, the topics that we are going to discuss today: manufacture of sulfuric acid H2SO4, ionic equilibrium, acid bases and salts. Then there are different theories for acid base: Arrhenius theory, Bronsted-Lowry theory, and Lewis theory. Okay, so all the theories will be discussed in detail. One manufacture process, which is Haber's process, in which we synthesize ammonia, that we have finished in the last class. And now the second manufacturing process, which is for sulfuric acid, and here the process by which sulfuric acid will be produced, that process is known as contact process. So in this process, there are basically total 3 steps, and one by one all the steps we will see. So the first step for the synthesis of sulfuric acid, it is burning of sulfur, or it may be burning of sulfide ores. So any of these two starting material we can use. So first reaction, as you can see, we have taken solid sulfur. In the bracket it is mentioned S, that means physical state is solid, and it is reacting with, as it is mentioned here, burning, that means it will react with oxygen gas and it will produce sulfur dioxide gas. Instead of taking sulfur, we can also take sulfide ores. Now, sulfide ores, in bracket it is mentioned pyrite. Pyrite is the ore of sulfur, which is basically the main component is FeH2. So we can start with FeH2 also. Now it is burned with oxygen, and after reaction we are getting here SO2. That means in the first reaction also we are getting sulfur dioxide, in the second reaction also we are getting sulfur dioxide. So this is the actual product that we are going to use in the next step, not Fe2O3. Okay, this is another product, but our requirement is SO2, not Fe2O3. So in either case, an excess of air we have to use, so that sulfur dioxide that is produced, it is already mixed with this extra oxygen, because in the second step we are basically going to do the reaction between O2 and SO2. So that is why already we are using excess of air, because in the next step it is basically reaction of SO2 with more of O2. So, and it will be producing SO3. So that is why already excess of air we are using. Second step, after the first step, the second step is, now starting material is SO2 in presence of O2. Now it will produce sulfur trioxide. Now this step is basically the important step in the whole contact process. Fine. So here it is mentioned, it is the crucial step. And this step, as you can see, reversible sign is there. Reversible sign is not present in the first step, right? But here we have this reversible sign. So this reaction, it is involving equilibrium. And here enthalpy change, that is minus 196 kilojoule per mole. That means it is exothermic reaction. Right? So here our product is sulfur trioxide. Now the third step, sulfur trioxide. Now finally it is converted to H2SO4. Now one question may arise, why we are not doing the reaction directly between SO3 and water so that it can produce H2SO4? We are not doing that. But what we are doing? We have already taken some previously prepared H2SO4 liquid, and this H2SO4 is reacted with SO3, which is produced in the second step, and we are getting this product which is called oleum, H2H2O7. Now this oleum, when it is undergoing reaction with water, now it is producing 2H2SO4. So the question may arise, why we are not doing, why we are making it so difficult, why we are not directly doing the reaction between SO3 and H2. Actually, what happens in this reaction, if we want to do, there is huge amount of heat liberated, and as a result, this SO3, because of that heat, there is a generation of fog of SO3. So because of this fog of SO3, there will be problem in the reaction. So that is why we do not, and because of that heat generation, water is also converted to steam. So these are the problems To avoid the problem, what we do, we react SO3 with previously prepared H2SO4, and we first make H2H2O7 oleum, then this oleum is reacting with water and we are getting finally H2SO4. But here in this manufacture process, as our focus is to the fact that how by involving Le-Chatelier principle, we can maximize the amount of H2SO4. Now in these three steps, as this is the crucial step, because only this step is involving equilibrium. I am writing in short EQM, that means it is only involving equilibrium. So if somehow we can make this step fast, obviously it will have the overall effect, that is in the overall yield of this H2SO4. So our purpose here is to focus on this second step, which is basically the crucial step, because that is the equilibrium step, where we can apply Le-Chatelier principle. That means we can control pressure, volume, temperature, and by controlling all this, we can maximize the amount of SO3. If somehow SO3 is maximized, so obviously the third step, we will get high yield of H2SO4. Okay. So here this pictorial representation for these three steps. In this pictorial representation, as you can see, first step, here we have dry air, which is basically containing oxygen gas. So directly oxygen is not written, it is written dry air, and sulfur is introduced and we are getting SO2. So this is the first step. Now in the second step, that is actually the crucial step where SO3 is produced. Here we are using all these conditions. In the next slide, we are going to do the detailed discussion about these conditions, that is catalyst, temperature, as it is mentioned here. Now the third step, here concentrated sulfuric acid is introduced, and this SO3, it is reacting with this H2SO4, it is producing first H2H2O7, which is basically called oleum, and then this oleum is reacting with water and we are getting finally H2SO4. Okay, so these are the pictorial representation. Next, we are going to focus on the second step. So this is the second step, right? At normal condition for the second step, which is crucial step, the equilibrium lies far to the left. It means what? It means it will mostly, that is once the equilibrium is reached, in the reaction mixture, mainly there will be presence of SO2 and O2. That means SO3 amount is very, very less. So our purpose is to maximize the amount of SO3 and to minimize the amount of reactants, that is SO2 and O2. So to improve the yield of SO3, following conditions are chosen, and that is on the basis of Le-Chatelier principle. Fine. So the first effect is effect of pressure. So if you look at this reaction carefully, in the left hand side, we have 2 moles of SO2 gas and 1 mole of O2 gas. That means total 3 moles involved. 3 moles of gas, obviously. We are interested only in gas molecules, not liquid or solid. And in the right hand side, we have 2 moles. That means as we are going to the forward direction, the number of moles of gaseous components is decreasing. That means the forward reaction will be favored if we increase the pressure of the system, because when we are increasing the pressure of the system, according to Boyle's law, remember these two are inversely related to each other. So you are increasing pressure, obviously volume, system will try to decrease the volume. And which side volume is less? Obviously towards that side where number of moles less. So that is why it will prefer the direction where lesser number of moles involved, which is formation of SO3. But we also have to take care of some other facts, that if you increase the pressure very high, there is some other problem. What is that problem? The iron towers which is used in this process, there will be a chance of corrosion, and that is the reason the process is carried out at optimal pressure, and that pressure is around 1 to 2 atmosphere. Okay, we cannot increase to very high amount because to avoid this problem, as it is mentioned. So we keep it between 1 to 2. Effect of temperature. Remember, this reaction we have seen here, delage value is negative. Now, when delage value negative, that means it is exothermic reaction. And for exothermic reaction, that is the forward reaction is exothermic. High temperature, backward reaction will be favored. So that obviously we do not want. So we will try to decrease the temperature. But remember, if you decrease the temperature very low amount, then kinetic problem may arise. What is kinetic problem? The same thing we have also seen in case of ammonia. That is, if we decrease the temperature to a very low extent, then the requirement of activation energy, that purpose will not be full. So we cannot decrease it to very low value. So we will keep it around optimal temperature, which is around 450 degrees centigrade. Though it at a first glance it may seem that it is very high temperature, but actually see, high, low, all these things are basically relative. You cannot say that it is 450 because we do not know what is the standard of low temperature. There is no such thing. So 450 is that temperature. It is already observed from, that is from the experimental result, that if we maintain temperature around this value, then maximum amount of SO3 is obtained. Okay, so don't think this is very high temperature, because sometimes in manufacturing process even temperature greater than 1000 may also require. Okay, so this temperature we have to maintain. And what about catalyst? To increase the speed of the reaction, obviously it has nothing to do with equilibrium, but as we are here, our purpose is to increase the yield of SO3, and we also, that is direct yield increase, that is not related to catalyst. Catalyst is basically helping in the kinetic factor. It will increase the speed of the reaction. So as it is manufactured process, obviously will expense should be very low. So if we can somehow the reaction speed we can increase by applying, using some catalyst, obviously that is preferred. So that is why we are going to use the catalyst, vanadium pentoxide P2O5 or platinum metal. Fine. So this is the manufacture process of sulfuric acid, which is also known as contact process. Remember this name, because if it is in the problem, if it is directly not mentioned that it is synthesis of sulfuric acid, suppose simply mention contact process, that means it is actually manufacture of H2SO. Okay. Related to this manufacture process, here we have this problem, and it is asking for this reaction 2SO2 plus O2 producing 2SO3. So remember, this is a second step of contact process, isn't it? Deluge value is mentioned. It may seem that why this value is different, because it may vary with temperature. Okay, so Kc value it may vary, deluge value may vary, but temperature is not mentioned here. But even these values are, it seems different, as it is mentioned in the slide where it is mentioned around minus, remember it is mentioned minus 196. Okay, so it may vary, that is in some question or in other textbook it may vary, because temperature matters. Okay, so whatever it is, it will not have that is because of this data will not have any problem. Okay, so ignore that. So important point is that deluge value, that is negative, that means it is exothermic. This point is important, not the exact numerical value. And Kc value, look, 10 to the power 16, it is very, very high. Now, under these informations that are given, you have to find which statement out of these four is false, incorrect. So come to the statement one by one. The first statement is saying that equilibrium will shift in forward direction as the pressure is increased. Now here we have in the left hand side 3 moles, and here we have 2 moles. So obviously if you increase the pressure, the equilibrium will be shifted towards forward direction, because here volume is less. Pressure high, volume less, that means number of moles less, that side preferred. So this statement is basically correct. This cannot be correct option. Second statement, addition of inert gas at constant volume will not affect the equilibrium constant. Remember in the last class in the Le-Chatelie principle, when we have discussed, we have seen when you are adding inert gas, there are basically two conditions you have to consider: whether you are adding the inert gas at constant volume condition or you are adding at constant pressure condition. If it is constant volume condition, there is actually no effect on the equilibrium. So that is why this statement is also true. Third statement, equilibrium constant is large. That is fine. It is already given. Suggestive of reaction going to completion. That it is saying that Kc value is high, so it will go to completion easily. So we don't have to use any catalyst, right? Now, if you are having any doubt in this statement, just keep this statement for some time and come to the fourth one. Because if you when you have 4 options, in any statement, maybe you have some doubt. So just leave it like that. Come to the fourth one. The fourth one is saying that the equilibrium constant decreases as the temperature increases. Now, obviously that is true because it is exothermic reaction. So if you are increasing the temperature, obviously the Kc value that will decrease. That means yield of SO3 will decrease. So this statement is also true. Now, if this is also true, obviously only one option is left, which is third option, and that must be false. So see, even if you have any doubt, just by eliminating options 1, 2, and 4, then also you can reach the correct. Now, okay, it is fine, it is correct, but why it is correct? Now, the reason behind it, why it is correct, it is saying that it is going to completion, Kc value high, so catalyst not required. But catalyst has nothing to do with Kc, right? Catalyst we use to speed up the reaction. Okay, the yield is fine, yield of SO3 is very good, but suppose if it is taking very, very long time, obviously that is not profitable, and we have to take care of the profit because it is manufacturing process. So catalyst we have to use just to speed up the reaction. It has nothing to Kc value high. It has no direct relation with catalyst because that is related to kinetics. So equilibrium constant has no relation with catalyst. Catalyst affects the rate with a reaction, with which a reaction proceeds. Okay. So it has effect only on rate. So in this case, we have already seen either V2O5 or platinum used as catalyst. So this is no catalyst required. This statement obviously not true. So the third option, that statement is incorrect. So we are done with Le-Chatelier principle, its application, which is basically manufacturing process of ammonia and H2SO4. Now we are starting ionic equilibrium. So up to this point, that is equilibrium chapter, we have seen different examples of equilibrium. But now the part we are starting, which is obviously equilibrium, because the chapter is all about equilibrium, but now we will deal with ions. That is why it is ionic equilibrium, and acid, base, everything will be under this ionic equilibrium. Equilibrium involving ions in aqueous solution, that is actually ionic equilibrium. The Michael Faraday classified different substances into two categories based on their ability to conduct electricity. Now, one category will be that substances that will conduct electricity in aqueous solution, and the category we will call electrolytes. But the other category which will not conduct electricity, that we will call non-electrolyte. Fine, two part substances based on whether they are conducting electricity in aqueous solution or not. Now this electrolyte, further classification is possible, whether it is strong electrolyte or weak electrolyte. Now there are three substances next we are going to discuss in detail: acid, base, and salt. Now these three substances, they come under this category of electrolyte. Now it may be strong, it may be weak, that is different, but remember these three, they are electrolytes. Okay, so there will be some presence of ions and they will be able to conduct electricity, so they are electrolytes. So electrolyte, if we see the definition, chemical substances which can conduct electricity in their aqueous state, or it may be in molten state also, we will call them electrolytes. Now how they are carrying this electricity? It is because of due to movement of ions, as they are carrying some ions, and because of the movement of those ions present in them, they will be able to conduct electricity. What about strong and weak electrolyte? How we are, what is the difference? So electrolytes which dissociate almost completely into constituent ions, that electrolyte is strong. Complete dissociation. Examples here we have all type of salts, though there are some exceptions. Two exceptions are mentioned here: HgCl2, CdBr2. These two are also examples of salts, but they are not strong electrolyte. But mostly all type of salts are under strong electrolyte category. Then we have mineral acids. So these are called mineral acids, and bases like NaOH, KOH. So when these acids, that is HCl, H2SO4, they are dissociating, their dissociation is complete. For example, if you take HCl, it will dissociate to H plus and Cl minus. So if I am, for simplicity, suppose I am saying in the container there are total 10 moles of HCl, and out of these 10 moles, suppose 9 moles are in dissociated condition, or it may be 10 moles dissociated condition. So obviously it is strong electrolyte. But out of this 10, if only 1% is in dissociated condition, so obviously you cannot call them strong electrolyte. And bases also like this, NaOH, KOH, when they will dissociate, it will be Na plus, K plus, and HO minus. What about weak electrolyte, which dissociate to a lesser extent in aqueous solution? They are called weak electrolyte. Examples are all organic acids. Here you have seen mineral acids, or you can call them inorganic acids. So these acids are basically inorganic. Chemistry will see this type of acids. But organic acids, that is carbon, hydrogen, will be there. They are basically under the weak electrolyte category. Exception is there, which is sulfonic acid. So sulfonic acid, it is basically containing SO3H. It is very strong acid. So sulfonic acid, in general, I can write it like this: RSO3H, where R group may be any hydrocarbon part. It may be CH3, CH3CH2 like this, or any larger alkyl group. So when except this case, because this is very strong, it will dissociate almost completely. So except these acids, if you consider other organic acid, for example, acetic acid. So in this case, its dissociation to CH3COO minus and H plus ion, this dissociation is very low. So it is lesser extent. So that is why they will be under weak electrolyte. And some bases like NH3, NH4OH. NH4OH is basically NH3 plus water. So when it reacts with water, its aqueous solution is basically NH4OH. And different types of amines. For example, RNH2. R is any alkyl group. Suppose CH3NH2, methylamine, or dimethylamine, that is Me2NH. So these type of amines, they will also be under weak electrolyte category. Fine. Now we will go into the details of acid, bases, and salts. So acid, bases, and salts, they find widespread occurrence in nature. In day-to-day life also, you will see many examples. Some pictures you can see in the right hand side. Hydrochloric acid, see, in biological process it is involved. It is present in the gastric juice and secreted by the lining of a stomach in significant amount. Look at the value, 1.2 to 1.5 liter per day. And it is very important for digestive process. Then we have vinegar. Main component is acetic acid, which is organic acid, CH3COOH. So these are the two examples. One is already involved in biological process, and also HCl we use in household requirement, and vinegar also it is sometimes used in cooking and also in other household requirements. Acid tastes sour. There are some basically general properties of acid, like it tastes sour, it turns blue litmus paper to red color, and it can react with some metals, not all metals. For example, when it reacts with zinc, suppose HCl you have taken, it is reacting with zinc, there will be production of hydrogen gas. That means the hydrogen that is present in HCl, that hydrogen, it will be removed to HCl. It will be H2 gas. Okay, so this type of reactions are common, you can expect from acid. And base, very common example, washing soda, detergent. Washing purpose it is used. It is basically sodium carbonate with 10 molecules of water attached to it. If you are, that is, when you say washing soda, the formula is like this. But if you simply you are saying that sodium carbonate, then the formula is N2CO3. But for washing soda, it is always with 10 molecules of water. The term acid is derived from the Latin word acidus. So this Latin word is, it means basically shower. And as we know, it tastes sour, so that is why the name is like this. Similarly, base tastes bitter and turns the lead litmus paper blue. Now these are some general, that is most of the cases you can see this type of observations, though there are some exceptions. That is, if you broadly consider the definition of acid or base, sometimes this type of test, it may not be there also. So we will also see some theories for acid and bases. Total 3 theories will be there: Arrhenius theory, Bronsted theory, Lewis theory. So there you will be able to see different types of acid and bases. Mostly when we say acid, the picture comes, that is the image that we think is HCl, H2SO4 like this. Or when you talk about base, the first name comes to our mind is NaOH, KOH like this, or N2CO3. But it is acid and bases, they are not just limited to these 3 to 4 compounds. There are different types of acid bases possible if we broaden the definition. So there are different theories, and all these theories you will see as we move from Arrhenius to Bronsted to Lewis. Gradually the definition, it will be more and more general. So it will be widened, broadened. Fine. So these are very common observation for acid and bases. Very in simple statement we can say, but it is not so simple. Fine. What about salt? When acid and bases are mixed in right proportion, they react with each other to give salt. So here it is mentioned salt and water is produced. That is, when you are mixing these two, there is production of salt and water. Some commonly known examples of salt: sodium chloride, BaSO4, and NaO3. So just take this example, NaCl, how you will get. So you are mixing HCl and NaOH. So Na and Cl, these two together, it will produce NaCl, and H and OH, these two together, it will produce water. Then if you are considering the example BaSO4, now the acid will be obviously H2SO4 sulfuric acid, because we need sulfate ion, and the base will be BaOH whole 2. Now these OH and H together, it will make water. Now if we generalize the concept of base in theories, the 3 theories, you will see different examples. In some cases, acid-base reaction, it may not produce water. So water production is only possible if there is presence of H, that is H plus ion should be produced from acid, and HO minus should be produced from base. Then only water will be produced as byproduct. And mostly in most textbook, you will find that salt and water is, that is, water is always the byproduct. But there are also some examples of acid and bases that may not produce water as byproduct. There must be presence of H plus and HO minus. These ions must be produced from acid and bases respectively. Then only you can get byproduct as water. But there are some examples of bases where you will not find any HO minus ion after dissociation. There are some examples of acid where you will not find H plus ion after dissociation. So in those cases, obviously water will not be produced. But in general, we see that is this type of representation, that is acid plus base, it is producing water and salt and water. Salt is the main product, water is the byproduct. Fine. So the first theory is Arrhenius theory. But before going to that, see this introduction. These classical concepts are not adequate to explain the complete behavior of acid bases. Which classical concept? The previous slide, whatever information you have seen related to acid and bases, that is basically classical. That is, it will convert red litmus to blue or blue to red. It will taste like this. It will produce H plus. So these are some classical concepts, but that are not adequate. Right? So scientists developed the acid-base concept based on their behavior, and the concept were developed by scientists. The first theory is Arrhenius, the second theory is Bronsted-Lowry, and the third one is Lewis, to describe the properties of acid and bases. This is number 1, number 2, and this is number 3. So you will see Arrhenius. When you will move from Arrhenius to Bronsted-Lowry, it will be gradually broadened, and when you will move from 2 to 3, then it will be further broadened. That is, the concept will be gradually broadened from 1 to 2 to 3. One of the earliest theories about acid and bases proposed by Arrhenius, and according to him, an acid is a substance that will produce H plus once it is dissociated. That is the definition of acid. Here we have examples. All these acids, as you are seeing, these are inorganic acids or mineral acids, HCl, HNO3, H2SO4. All of them will produce H plus ion once they are dissociated. So from H2SO4 you are getting 2H plus because there are total 2 hydrogens, and you are getting SO4 2 minus sulfate ion. In this case it is H plus Cl minus. Similarly, if you take nitric acid HNO3, you will get H plus and nitrate ion NO3 minus. This H plus ion in aqueous solution that remains highly hydrated. So these reactions are basically occurring in water medium. Now in water medium we have H2O. Now this H2O, it will react with this H plus and together it will produce H3O plus, which is basically combination of H2O and proton, that is H plus. So that is why we are saying H plus in aqueous solution, it will remain in highly hydrated state, and hydrated state of H plus is basically H3O plus. So it is represented like this, and its name is hydronium ion. Now from this, as we are that is further discussion will be as we will proceed in the next classes based on this ionic equilibrium. Mostly you have to consider that sometimes H plus will be used, sometimes H3O plus will be used, but actually they mean the same thing, fine, proton or hydronium ion. So this is all about acid. What about base according to Arrhenius? Similarly, a base is a substance that dissociates to give hydroxyl ions HO minus in water. So once the base is dissociated, there must be presence of HO minus. So here we have examples: sodium hydroxide, barium hydroxide, calcium hydroxide. So Na, as its that is oxidation state is +1. So only one HO minus. For Ba it is 2 plus. So there are total 2 HO minus. For calcium also same thing. So BOH whole 2, we are getting one barium 2 plus cation, but this presence of hydroxyl ion, that is important. Otherwise, you cannot call them Arrhenius base. And for acid, if there is no H plus after dissociation, you cannot call them their Arrhenius acid. Fine. Arrhenius theory, it has some limitations also because it is the most narrow theory. Why I am saying narrow? Now you will understand. This theory doesn't explain the behavior of acid and bases in non-aqueous solvent. So in the previous definition, what we have seen, that it must be in water medium. That is the dissociation we are talking about. So you have taken HCl in water. You can also directly write water like this. And in this case, H plus, it will directly combine with this. So I will write here H2O plus. I'm not writing H plus, I'm writing H2O plus and Cl minus as usual. So these reactions are taking place in water medium. Fine. But suppose the same reaction, you have taken HCl in acetone, which is organic solvent. Formula for acetone is CH3CO CH3. Or you may take it in some alcohol like ethanol, CH3, CH2OH, or you can take it in sulfur dioxide. So all these are basically non-aqueous solvents. These are also other examples of solvent. When we say solvent, the first thing appears in our mind is water, but that is aqueous solvent. But there are so many other types of solvent except water, and you will call them non-aqueous solvent, obviously. But this definition is you cannot explain, because when you have taken HCl in acetone or SO2, this type of production of H plus, that is H3O plus hydronium ion, is not possible. So that is why this theory now it is limited. It is not possible to explain if it is solvent other than water. There is another problem. The theory doesn't account for the basicity of the substances like ammonia. So we have seen the definition that there must be production of HO minus. So that means before dissociation there must be HO minus ion. But look at this basis. There is no presence of HO minus. Sodium carbonate, ammonia. There is no presence of HO minus group. So how to explain? Are they not base? But they are also base. But according to Arrhenius, we cannot call them base. So this is limitation. Similarly, acidity of substances like oxides of carbon, sulfur, N. Here you do not have any H plus R. They cannot produce H plus R. But still there is behavior of acidity. So their behavior of acidity you cannot explain on the basis of Arrhenius. So you need some other theories because here we have some limitations. So to explain acidity of these molecules, Arrhenius theory is not enough. We need some other theories. Fine. So we will see in the next two theories whether we'll be able to describe, we'll be able to overcome these limitations. Fine. So the second theory is Bronsted-Lowry theory. It is also called proton theory. Why? In the previous case, you have seen the definition that acid must produce H plus or H3O plus. Base must produce HO minus. As if acid is H plus producer, base is HO minus producer. But in Bronsted theory, it is totally based on proton, that is H plus. So Lowry and Bronsted suggested a more general definition. So now it is compared to Arrhenius, it is the concept is now broadened, widened. Okay? Definition is widened. More general definition, according to their concept, acid is defined as a substance. It may be molecule or ion. That means, now see, in the previous case when you have started, that is when we have seen the definition, all the examples we have seen, they are neutral molecule, HCl, H2SO4, NaOH, BaOH whole 2, everything, all the molecules are neutral. But in this case, we have mentioned in the bracket, it may be molecule or ion. That means it may be neutral or it may be some cation or anion. So obviously now it is more general, right? So it is a substance, acid is a substance, it may be molecule, it may be cation, anion, mostly cation when it is acid, that has a tendency to donate a proton to another substance. And on the other hand, base will be a substance, molecule or ion, that has a tendency to accept proton. So in simple words, you can say acid is proton donor and base is proton acceptor. This is the main, in simple word, that is the definition. So broader definition, now we have compared to Arrhenius. Now we will see some examples of acid and base based on Bronsted. So these examples of acid that we are going to see, obviously they should produce H plus because they have to donate H plus, right? Then only we can call them Bronsted acid. So see, these are the examples. First we have some neutral molecules, so we are calling them molecular acid because they are simply molecules. HF, H2SO4. So these examples you have also seen in case of Arrhenius because they are also fulfilling the criteria of Arrhenius. Then we have acetic acid, water, H3PO3. So these are the examples of Bronsted-Lowry theory. Now, acid part, basically the definition you can find similarity with Arrhenius. In Arrhenius also we have seen, they can just see, yeah, the definition we have seen that they dissociate to give hydrogen ions. So in this case also we are saying it is proton donor, so it is having some similarity from acid point of view. And ionic acids examples, so see, we have some cations, we also have anions. Don't think that anion it cannot behave as acid. No, it may not be so. You just have to check whether they are able to give H plus or not. That is the definition. Whether it is cation, anion, that is not important. So in this case, we have these examples, H2O plus. The hydronium ion itself is also acid because it can donate H plus. It can also, that is H plus and H2O. This will be produced when it will dissociate. Similarly, NH4 plus. Plus sign is basically over nitrogen. So when it is, that is, if it is giving proton, it will produce this neutral molecule and it will produce H plus. Similarly, H3O plus, it will produce one neutral water molecule and H plus. So it is giving H plus. So that is why it is proton donor, right? And molecular acid, we also have example of H2O because H2 also you can consider it as if it is giving H plus and HO minus. Now question may arise that H2O, the rate, that is the tendency of H2O to give H plus and the tendency of H3O plus to give H plus, are they same? See, now that depends on what type of other substance are present with them, because when they are donating proton, obviously there must be a second substance which will accept this H plus. Now depending on the nature of this second substance, suppose with H2O we have X. I do not know what is X. Suppose X is present. Now depending on this nature of X, how fast H2O can donate H plus, how fast H2O plus can donate H plus, that depends, that may vary. So if X, its H plus accepting capacity is very high, obviously H2O can easily give H plus. So that is why the other substance, how fast it can accept H plus, that is also important. Now this X is basically Bronsted base, because what is the definition? It is proton acceptor. So now we will see the examples of bases. Molecular bases, that is neutral, where we have amines. See, water is also molecular base. That means it can behave as acid, it can behave as base as well. So as I was saying, what is the other substance present with it? Suppose with H2O, some other substance X is present which can accept proton. So in this case, obviously it will behave, H2O will behave as acid. But in this case, suppose with H2O we have Y, some other substance which can, that is in this case H2O will accept proton because it is base. That means Y should be proton donor. So depending on this other substance, H2O may behave as acid or as base. Not just H2O, there may be any other type of, that is this type of behavior you can also have for some other molecule. So this is a special behavior, that is same substance, depending on the other substance with which it is present in the medium, depending on that its behavior may change. Now some ionic bases, look at these examples. HO minus, so it can accept proton, so that is why it is ionic base, HO minus. Then sulfide ion, it can accept proton. Carbonate ion, it can accept proton. Mostly we have here anions. So NO3 minus, when it will accept proton, there must be some proton donor, so it will now produce HNO3. Okay, so these now you can see this is more general theory compared to the previous one, right? So this theory further will extend the discussion. It is important to note that no single substance is an acid or base. So whenever you are talking about acidity, there must be some other substance which is behaving as base. It is not a single process, right? Both will be happening simultaneously, acid behavior, base behavior. So acid or a base as a single substance, its presence not possible. So no single substance is an acid or a base, as a single substance cannot donate a proton until and unless some other substance is there to accept that proton which it is donating. So when you are talking about some proton donor, there must be some proton acceptor, and that is actually base. So in the left hand side we have proton donor plus proton acceptor. We are calling them, in the bracket it is mentioned acid and base. But when you are going to right hand side, so it is 4. Now proton donor you are getting. Now this proton donor is it has given proton. So now it will have now base type of behavior. So now it is behaving as proton acceptor, and the proton acceptor that it has accepted proton. So now it has proton, it can now donate proton. So from this point of view, left hand side, this is one type, acid base, but on the right hand side you will have another acid and base. With example you will get clear idea. So when hydrogen chloride is dissolved in water, it donates a proton to the latter. That means HCl is donating proton to water molecule. See, so HCl is acid, H2O is base, according to the definition. Now, after H2O, it has accepted proton. Now it is H3O plus. So this is also another type of acid, because if you look from right hand side to left hand side point of view, H3O plus, it can protonate Cl minus and it can move towards HCl. And HCl left hand side it is acid, but after proton donation now it has converted to chloride ion. So it will now be base. So just try to find similarity with this one, because this is general equation written and this is actual example. Fine. Now question is that whether the equilibrium will be towards left or right, but we'll come to that point later. That depends on stability actually. Whether H3O plus is more stable, that is Cl minus H2O plus is more stable, or the species that are in the left are more stable. That is different thing. But important point, try to focus that in the left hand side you have one acid base pair, right hand side also you have another acid base pair, and the pair that you have in the right hand side, they have a special name that we'll also see, and they are actually called as conjugate base and conjugate acid, right? So we'll come to that point later. Now another example, when you have taken ammonia, you are dissolving it in water. Now ammonia will accept proton from water. In the previous case, base is H2O in the left hand side, but in the right hand side now we have H2O plus. In this case, H2O is acting as acid and this is base, and now it has become acid and this is base, right? So in this example it is clear that same molecule H2O, whether with it HCl is present or ammonia is present, depending on that, it can behave either as acid or base. So water is acid with respect to ammonia and it is base with respect to acid, HCl. So this type of substances which can behave in both ways depending on the other substance, we call them, both ways means which can act as proton donor or acid as well as base or proton acceptor. We have a name for them and that is amphoteric or amphiprotein. So H2 is example that we have seen here, but another example is bicarbonate HCO3 minus. So HCO3 minus, it can accept proton and it will be converted to H2CO3. Similarly, it can donate this proton and it will be converted to carbonate ion, now 2 negative charge. HSO4 minus, after accepting proton, it will be HSO4 molecule, neutral. But it can also donate proton because it has already one H. And after donating proton, it will be SO4 2 minus. Okay, so these are the examples which are basically amphoteric substance or amphiprotic substance. Okay. Now we will see conjugate acid base pair. So same example we have taken again, water reacting with ammonia. It is acid here, it is base here. Look at the right hand side. H2O, after donating proton, it is converted to HO minus. These HO minus we will call them conjugate base of acid water. Okay, so this is actually these two are pair which you can see here. So conjugate acid base pair or simply conjugate acid base. So H2S acid and HO minus, this is conjugate base. So in conjugate acid base pair, there will always be a difference of H plus. So in one substance there will be H plus present, another substance there will be H plus missing. Similarly, if you consider ammonia, it is behaving as a base in the left hand side, but after accepting proton, it is now converted to NH4 plus. So this is the conjugate acid of NH3. So that is why you are calling them conjugate acid base pair. This is ammonia and this is NH4 plus. So these white balls are H, this blue one is N. Here we have 3 hydrogen, here we have total 4 hydrogen. Similarly, this is oxygen and hydrogen, and this is oxygen and H, only 1 hydrogen. Fine. So this is the conjugate acid pair, acid base pair concept. When an acid loses a proton, the residual part So residual part of H2O after H plus donation is HO minus. Residual part of it will have a tendency to accept a proton, leading to its behavior like a base. So this residual part HO minus, it can also accept proton, so leading to its behavior like a base. And such pairs of substances which differ from one another by a proton only, they are called conjugate acid base pairs. If Bronsted acid is a strong acid, suppose the top acid, Bronsted acid we are talking about, it is very strong. Just take the example of HCl. Compared to H2, obviously it is strong because its tendency to donate H plus is high. Now it will dissociate as H plus and Cl minus. This Cl minus is basically the conjugate base of HCl. Now here it is mentioned, this point is very important, please focus on this. It is not just important for equilibrium, that is in organic chemistry also you will find its application. That is for in general for chemistry it is very important fact. If Bronsted acid is strong acid, conjugate base will be weak and vice versa. So in this case HCl, it is in water medium, it mostly remains in dissociated condition. That means it is strong acid. So its tendency to dissociate to H plus Cl minus is very high. So equilibrium it will be mostly towards right hand side. Now if the equilibrium is mostly towards right hand side, I am writing this arrow in this way. This arrow is longer, this arrow is shorter. That means it will mostly remain in dissociated state. Now in this case Cl minus is basically very stable. Now when I am saying something stable, that means it is weak, and here it is strong, that means it is unstable. So strong, unstable or reactive, anything I can say. And this is not so active, this is non-reactive, relatively obviously. So it is stable, that means it is weak. So when your acid is very strong, the conjugate base has to be weak, because as it is weak, that is why it is stable, and as it is stable, that is why the equilibrium can easily shift towards right hand side, because in the right hand side it is finding some species which is very stable, and any system will try to remain towards that side where stable species are present. Okay, so that is what is mentioned. Whenever you will have any strong acid, its conjugate base has to be very weak. So why this fact is important, and vice versa obviously. If suppose this acid is not so strong, so conjugate base in that case it will be unstable, it will be very reactive, that means it will be very strong. All these are, it means same thing, whether you are saying in terms of stability, in terms of weak or strong, or in terms of reactive or non-reactive, everything is basically same. So vice versa, right? So why this fact is important? Suppose you have two acid given to you, one is HX, another one is HY. So in the first case conjugate base is X minus, in the second case conjugate base is Y minus. Now if it is asked that among these two which one is more strong, just look at their conjugate base. If you know conjugate base stability, if you can compare, suppose in this case you know that X minus is more stable compared to Y minus. Now X minus more stable means what? HX will mostly remain in in dissociated state, but Y minus is not so stable like X minus. That means it will not remain in dissociated state like the previous example. So now we can say as X minus is more stable, obviously acidity of HX is higher than HI. So just looking at the stability of weak base, that is stability of bases, when 3 to 4 acid examples are given and you have to find their order of acidity, so it can help you, and vice versa. If you know which acid is more strong, suppose you already know HS is stronger than HY, so now you can say that X minus will be more stable, that is X minus is weak compared to Y minus, that means X minus is more stable. Okay, so this point is very important. So that is all about Bronsted theory, but here also we have limitations. In Arrhenius we have seen limitations. Now this theory is more general compared to Arrhenius, but still we have limitations. Substances like BF3, AlCl3, etc. You will not find any proton, there is no proton to donate, but they are also behaving as acid. But how we will explain on the basis of Bronsted theory? It is not possible. But that we can do in the next theory, which is Lewis theory. So the limitations that you have in this second theory, we can overcome in the third theory. Fine. But that we'll discuss in the next. Today we are at the end of the session. Thank you for listening.